I'm Chris Kimmel with Humanity in Deep Space, and welcome to another one of our webinar episodes, which we've been doing now for about a year. These webinars are an attempt to bring together a lot of really interesting ideas and concepts and people that explore how we as humans are going to survive and thrive in deep space. And one of our objectives is to create a planetary conversation around these issues. Going into deep space, leaving our planet is in fact a planetary issue and problem. And we're very proud of the fact that our webinars not only attract hundreds of people in attendance, but also generally people from 25 to 30 countries all over the world. And so we are in fact beginning to gather together and get the ideas and in participation of people from around this planet, which is very, very important. Humanity in Deep Space is a new initiative that really looks at trying to create a planetary conversation around some of the very hard and difficult problems that we face once we become, or we already are, as we continue to become and transition to an off-planet species. Of course, we've had people in space, we've been to the moon, we've had people living and working in space for over a decade. So we really are already a spacefaring species. And there's a lot of difficult problems, a lot of technical problems with propulsion systems and other kinds of things, but there's also a whole range of under-addressed issues and problems that we face if we're going to do this successfully. Issues related to physiology, psychology, ethics, what are we going to eat, food, governance issues. And so there's a whole range of interesting issues that are equally important in having us do this and doing it properly. And so that's what's given rise to Humanity in Deep Space. I'm also the co-founder of the space company, Space Tango, and really in being immersed in a lot of the things over the past 10 plus years in commercial space is what got me and others thinking about some of these other kinds of issues that sometimes people think are tangential, but they really are central. Before we start, I'd like to thank our sponsors. Again, these are the organizations that make this possible. National Stem Cell Foundation, Kentucky Science Technology Corporation, the START program, 22 Solutions, Space Tango, Baird, private wealth management company, the Shelgren Center, Higher Orbits Media Collaboratory, and of course, Humanity in Deep Space. So thank all of you. So today we have, I think, one of the most interesting topics in the whole issue of are we built for space? And we have a great panel with us today, which I'm going to start out by asking each one to introduce themselves very quickly. And I'll start on my left, which is Dr. Church. George.
Yeah, thank you. I'm a professor at Harvard and MIT working on technology development, mostly for reading and writing DNA and anything biological or even non-biological that's downstream of that, ranging from organs to ecosystems to therapeutics and diagnostics.
Great. Dr. Wu?
Thank you. I'm a professor of genetics at Harvard Medical School. My lab studies a number of things genetic. The one that might be most relevant to today's conversation are a curious set of sequences called ultra-conserved elements that we think may help protect us in the distant future against radiation damage. In addition, we invent technologies for imaging the genome at very, very high resolution. And the other piece that might be relevant to us today is that I direct the personal genetics education program, which aims to have everybody on our planet become aware and be able to participate in conversations about genetic technologies.
Great. Dr. Mason.
Hello, thanks for having me. And I'm a professor of genetics, physiology, and biophysics at Weill Cornell Medicine in New York City. And I have a laboratory that focuses a lot on the three main areas. One is clinical genetics, looking a lot at how cancers evolve genetically and epigenetically, and then also clinical genetics for astronauts. Very relevant for the discussion today is what happens to astronauts when they go in space. How do we bring modern clinical care to the astronauts that are both private and government funded? Then we do also a lot of work in computational biology and algorithm development. And the third area of the lab is in systems biology and doing some engineering of cells to mix and match between evolutionary lessons from different creatures on this planet and maybe someday others. But right now trying to do a lot of cell engineering, again, also sometimes for very focused clinical questions like cancer therapy, like custom T cells, and also in other cases, very fun projects like taking tardigrade genes and seeing if they can work in HEK cells, for example. So very exploratory lab.
And you're also a lead on one of the leads on the twin study, correct?
Yes, was one of the PIs. It was a big group effort, so I was one of 10 different groups who all worked on the twin study. Also was the lead geneticist for the Inspiration 4 mission, which just launched, and been working with SpaceX on their medical program. I also chair the Gene Lab program at NASA, which is looking at a lot of animal models for spaceflight. And then also just recently for the on the National Academy of Sciences Decadal Survey, which is trying to figure out what we recommend to NASA for the next 10 years. What should they be focusing on? So I'm actually, if anyone has any ideas, the members are supposed to solicit as many thoughts and opinions as possible about what should we tell NASA and other space flights and companies, agencies to do for the next 10 years, which I recently wrote a book called The Next 500 Years, which is part of that, I'd say.
Yeah, great, terrific.
Total shameless plug, but yes.
Yeah, that's right. I've got the book. I'll put it up here, just like David Letterman. I'll get it up here.
That's right.
So in any case, I'll also let you know that these are recorded. And so if you miss some of it or all of it, you can go on our YouTube channel, usually about 24 hours later, and you can see this along with the other webinars on our YouTube channel. And also just another plug, NASA has been a great partner in the development of this series and throughout the series. We've had several NASA people as panelists, and they've been great all through as consulting in some of these topics. So those of you who want to ask questions throughout the seminar, you can ask them. We'll get to those during the discussion and then towards the end. So please feel free as you wish, and as you get stimulated, feel free to ask, pose questions to us, and we'll try to get those to the speakers. So to start off with, I think the big question, are we built for space? It's kind of a simplistic question, but of course we are the result of billions of years of evolution and all that that entails. And I think one of the big questions I know I've had and others have, particularly when we talk about deep space, is are we really physiologically actually capable of doing this? So let me start with Chris.
I'm going to just say no. I think at least not in a naked form. Even with a spacesuit, it would be hard. And we know we can survive in the short term, but built for implies that there's a function that's satisfied. And I think we know we couldn't just for example, just on the surface of Mars would be too much radiation. But if you go below, you would get some protection, and you could build a lot, I think, under the regolith. But we know that the humans are frail. Even on Earth, we can't. We're not built for Antarctica either. So to be fair, physically we're not built. But what I think what's extraordinary about humans is even if we're not actually built for something, we have an extraordinary ability to make ourselves adapt to it. And so I think even if we're not natively ready for it, our ingenuity lets us go places that we might normally not think you could survive, including space.
Okay.
But it requires technology, medicine, tools, engineering, all those things to bring to bear.
King?
I agree with everything you said. I think we are built up here to aim certain places. And there are times I'm so proud of being a Homo sapien, seeing what we can achieve when we really set our mind to it. I think, especially when we don't ask for perfection, we ask for practical capacity. I think it's pretty impressive. When you were talking, Chris, I was reminded of, is it the hermit crab that changes shells, right?
It jumps around, yeah.
Right. And all the organisms we know who take advantage of their environment to make themselves able to live in spaces that otherwise seem inhospitable.
Yeah, George, I know you did a lot of work with obviously you were in the middle of all this and still are CRISPR. I mean, not if there's any relevance there, but what are your thoughts?
Yeah, we've also been involved in making small sequencing devices for use in space with small payloads, working with NASA for decades. I think whether I must say whether we're evolved for rather than built for,
Right.
because we still haven't built a human being yet. But what worries me is the transition. That is to say, we can probably evolve ourselves or build ourselves further to adapt. But there are many cases where we've tried to adapt and have failed. And so what worries me is that we're going to do the experiment at a great distance from our current civilization, and so if something goes wrong with a largish colony, we're not going to have an easy way of fixing it, and even the small disasters like that occurred on the space shuttle, where a few people die, is enough to be really sobering and disruptive in every way.
Mm-hmm.
So just listing the things that could go wrong, and we've got even on a planet like Mars, we've got microgravity. It's not, and in fact, to some extent, it's easier to spin a spacecraft in space, although we don't do it except in science fiction. But in principle, it's easier to do that than to spin a large city or something on a planet with 0.4 times Earth gravity. We have issues with microorganisms, with ecosystems. We can make ecosystems that are very simple, but generally when they do, they become dysbiotic. If you clear out your body with antibiotics, you often get a dysbiosis, which is very bad. And the same thing happens with ecosystems. So I worry about that we're not going to take everything with us. And so the subset we take may not be the right subset. There are all kinds of psychosocial things. I mean, we can see how big a psychosocial event COVID-19 has been, with some of us locked up, one parent with 4 kids locked up and nowhere to go. And I think that could play out as well. And the list goes on. And there are opportunities too. But I think what's really missing is we don't have practice space colonies on Earth.
Right.
That would be a much safer route than what we're doing right now, which is focusing entirely on the physics of getting out there.
Right.
And not enough on having really sealed, no exchange with the outside environment. Even the ISS and submarines do a lot of exchange. So anyway,
I agree, and I think that the issue of the propulsion system, the technology, getting there and getting back are probably the easiest thing when you look through all of these things. So let me ask this. I mean, one of the things that not being an expert in this, I get to ask and think about things that are sometimes pretty nuanced, because like I said, I don't know any better. But there's trillions of moving parts in a human. I don't know, 32 trillion with cells and all these other kind of things. And I know we talk about the large things. We talk about radiation and all those kinds of things. And I know this is purely speculation, because no one's been in space beyond a year, and certainly not deep space. But it seems to me that there's a whole lot of things that could go wrong. in again, both in terms of the lack of exchange with nature, which I agree with, and the whole issue of deep space isolation, radiations, zero G environment, et cetera. I mean, how do we even think about preparing that, since there's no way to test any of this stuff ahead of going?
For which, you mean for the therapies to prevent it, or just even?
No, just the idea that like, I mean, what happened to the microbiome? I mean, there's so many things we don't know, and there's no way really for us to figure it out, because there's no way to test bed this stuff other than to put people in space.
Well, so I mean, I think to George's point, there was the biosphere, which tried to do it, and it is notoriously and spectacularly failed, at least in some of its metrics, because it's really, we could do more of those. They are called analog missions,
right?
But a real one here wouldn't be that hard to do. I mean, of course, it's funding, and NASA does fund some of these analog missions, so that,
right.
but they're not purely sealed, and so I think that is, a good point, that we could just start doing that now, but do it really rigorously, where you're stuck and there's nothing in, nothing out.
Yeah,
that would be good to do.
Of course, we can't mimic zero G, which is the big, the 100-pound gorilla. I mean, that's really the big thing. And aside from being isolated and things, the whole idea of the zero G physiologically and psychologically.
When you say, though, that the space station is a first step and the twin study was another step, these are giving us the first taste. I think about the initiation of many fields. Sometimes it was accidental, sometimes it was just a small window on which we can build. So it seems the twin study gave us some pretty interesting things to think about, let's say.
It definitely did. I mean, I think it was part of my, I think a lot of my enthusiasm for the project. It was the longest ever for a NASA astronaut. There has been some cosmonauts that have gone longer in space, I think 3 of them. Actually, if you've not been to it, everyone in this audience would certainly love it, but there's a website called Supercluster, which is a great summary of all kinds of data and metrics about all things in spaceflight. So if you haven't been to that website, it's really fun. It lists every astronaut that's ever been, for how many days, who's up there now. It's a really fun website. In any case, you can see this, but it was the longest for a NASA astronaut. And we could see, what was really great is some of the papers we published last year is that Scott Kelly, it was his 5th time up there. And so he, in some cases, his cortisol levels or some of the spikes that we would see other astronauts really have a hard time with, he did just fine, but other metrics changed dramatically. His microbiome changed, his telomeres got a little bit longer, he got 2 inches taller, although that was temporary. He lost that as soon as he landed back on gravity. And we saw a lot of fluctuations where most of them went back to normal when he got back to Earth, but some of the DNA damage we could see, even in his urine, we could see 8-oxoguanosine come out in the urine. You could actually see evidence of damaged DNA coming right out of his body. And we see this for most all astronauts. And so I think what's interesting is, a lot like we think of precision medicine for cancer patients in the hospital, we try to understand them as best we can and treat them all as unique molecular snowflakes. Although I'm still looking for a better metaphor, but right now that's what I'm going to go with, is that they're all actually quite distinct, very much like what happens with therapies today at hospitals. And so in terms of the molecular data, they're all pretty distinct. There's certainly some features that are consistent, like C-reactive protein or interleukin cytokines that are spiking up when you get into flight. So there's definitely a response that the body has to deal with. But over time, we could see that the plasticity of the body was relatively reassuring for Scott. So we think if you can keep a space station-like environment and keep him worked out almost every day, and he would actually say if he went one day without working out, he could even feel it in his bones. Like, I think if we go one day without working out on Earth, we're like, oh, I should get to the gym, but you can wait a day, or sometimes wait a week, or if you got a grant due or something. But in space, he said he could almost feel it, like his bones felt different. He wrote about this in his book, and then we could see calcium coming out in his urine. So like, I think he could.
So Chris, why don't they spin the ISS?
Just the engineering. I think if something goes wrong, it would be catastrophic, but it'd be catastrophic if something went wrong now on the ISS if there's a hole. So I don't know historically why NASA never did that. I mean, it would take very little energy to start it or to keep it moving.
And it would free up like 5 hours a day so you don't have to be on the treadmill. Right.
And space, you don't need a big treadmill, although it does fold up, but still the space, the weights, it'd be much easier on their body. But I can't speak on behalf of NASA as to why it's never happened.
Real quick, somebody asked the website again, the Supercluster?
Oh yeah, and I can't. The chat box is not enabled here. So
That's
otherwise
okay, but it's
It's
supercluster.
just supercluster.com.
yeah,
Okay.
just
All
it's a
right.
really fun website. Anyway, if you want to see who's been up the longest, who's
Yeah,
up
no,
now,
somebody asked that. Again, we talk about it, as Ting said, I agree the first step of but I want to come back to just the extraordinary difference between a year in low Earth orbit and 3 years on a Mars expedition. I mean, it takes 5 to 7 months to get there. You're going to have to, I mean, not literally, but figuratively, you can really only come and go every 2 years because of the orbital alignments and things like that. So let's assume, you're going to be there a year at least, and then 5 to 7 months back. It just seems to me that that's an enormous leap from what we have done and what we can even do in preparation.
Yeah, this is one of the big questions that I got a lot after we published the twin study was, does this look like can we use this as a model for the longer missions? And we have to say, it does indicate that there's a lot of stress on the body, but that it can adapt as long as you keep stress on the body and working out. But, I think it means there's no red flags for Mars. I think we could get there, we could survive if we had all the same framework and also protective gear of the ISS and get there and get back. But it would be hard on the body, I think, for sure. Even, Scott said that he didn't feel normal until about 6 months after he got back to Earth. And we could see some of that in his cytokine data and his gene expression data, even in how his, chromatin was organized. A lot of it was still adapting to being back on Earth. And so if it's a longer mission, I think we could survive there and back with the current technology.
Yeah.
Just to be harder on the body.
Several people have talked about, well, don't we, wouldn't we naturally evolve in space to this adaptation? And I'm sure ultimately we would. Whereas I guess one of the questions is, how long would that take? So let me throw that out there. Several people have asked that about the physiological system evolving.
I see in the Q&A box, someone has asked explicitly that. I believe there are a couple ways of looking at this. And Chris, you would know more about this physiologically, but there are many changes that happen within hours of reaching the destination space. Your blood pressure, your flow, everything, you get a lot more swelling in the head. But apparently that for most people, their body adapts and they're fine. And then when they come back down, they have to do the reverse process. So I think there's quite a bit of evidence that the human body, even though we, as far as we know, did not do much, go through a lot of evolution in space, can adapt. And so these changes that we see that are so frightening may actually be advantageous, I guess, one way to look at it. Mm-hmm. So I think at the gross level, there is such adaptability. Now, I think someone else was asking about genetic differences. Right. That's the question. That's what we have to look at. And that depends on N, your sample size. More people need to go up and be studied to see whether there are variants. There's so many variants on Earth that make you more or less able to withstand certain situations. So it's hard to believe that those variants would not also, some of them would not also apply in space. We just have to do the experiment or collect the data. It's probably a better way of putting it.
Yeah, somebody was referring to a question here too about obviously the experimentation that needs to be done on humans to do this, and can we do that ethically, and how do we do that? I think the other question is, since there's going 260 miles up, or even the moon. I mean, the moon is for 3 days away. You can always tell people you can send you can send people frozen pizzas on the moon, but not to Mars. I mean, would part of it be a mission where maybe a spaceship goes out 3 months into deep space and turns around and comes back instead of something like that? Would that be feasible, as opposed to just saying let's get it all and go to Mars and see what happens, and actually go out into deep space for a couple months and then come back and see what the effect has been? Does that sound halfway reasonable?
Yes.
I think yeah, definitely. And actually, if you've got funding, so what's great is Axiom is a new company building a private space station, and they're a commercial operation. So if you can pay for it, you can go up there as long as you want. We're planning one mission with them now of trying to get someone to go up in space for 500 days, which would be kind of the minimum Mars mission, and seeing if we could get that. And their answer is always like, well, if you can fund it, we can help fly it, because the goal is to have a fully commercial space station. Like if you want to rent out a hall for a concert or for a conference or a dance party, like well, we've got the place for you. Just tell us what you want to do and rent out the hall. is kind of the way they're viewing it, as a commercial space where you can do experiments, you can do manufacturing, you can have people live up there. So I think some of those kind of experiments, which would be almost impossible to do with NASA, or would require so much coordination,
Right.
it would take a while, or just difficult. But it would be, you could do it as long as you have the money, starting probably next year.
And then
I think
maybe,
Axiom 1 goes out in February, so it's one of the first ones.
and maybe a parallel program could be to talk to such individuals who are doing that, to see if they'd be willing to donate their physiological information, their genetic information, so that we can have them participate in a long-term experiment.
Yeah, and that's when we've started banking some of them. We did this for the Inspiration 4 mission. So we have an active IRB at Cornell, which is just for astronaut profiling and multi-omic monitoring, and it's for their life. Actually, the IRB, I first sent it to our IRB. I said, I'd like to have this be a lifetime study. And they said, how about we make it 5 years follow-up? And I said, no, it's for their life. I feel like this is where we're guarding and keeping track of their genome almost as a service. But the IRB said, let's just do it 5 years from now, and then we'll revisit so they can reconsent. But it's a fully active IRB, and NASA also has what's called a longitudinal health study for all their astronauts. But there's not as many, and they're not doing a lot of the same assays, but there's at least 2 efforts that are doing this. And I think all of the Inspiration 4 crew signed up for it, actually. So they've been really great test subjects, the 4 civilian astronauts who just went up last month. And they've been, I think most people, if you said, hey, can we take some blood and stool and urine and will you donate? Most people will. People are still the most afraid of stool, I found. They give you almost anything, but if you have to collect stool samples, that is ironically the hardest thing to collect so far.
Somebody asked a question about pharmacokinetics in space, drug metabolism. What do we know about that so far?
There's a really great article that was then called like the pharmacy of space. The majority of astronauts take at least one medication. A lot of it's for just sleeping, just to sleep better for the first parts of the mission. So most astronauts are on some kinds of medications, and they do seem to work, but there's a lot of anecdotal variegation of response. And some seem like they have to take more Ambien than they would feel like they normally would have to. But I don't think we know functionally why. We haven't looked at the pharmacogenomics genes, like the cytochrome P450 genes in each astronaut, and looked at the differences. So we know from what they tell us that there's differences, and they sometimes feel like they have to take more medication. Usually it's just for sleeping, but we don't know too much yet. We can see things in metabolomics, and that there's some differences, and even some potential genetic risk factors for SANS, which is spaceflight associated neuroacular syndrome. That kind of gets back to one of the questions of differences in ancestries. We know that females seem to so far have less eye damage from spaceflight, and we don't exactly know why. It's also a low sample number, but one of the hypotheses is that because the female body has to go through a lot more change during pregnancy, it can tolerate a lot more of that, but that's still low sample size.
Yeah, I wanted to get to that. When a number of people have talked about and made projections about, we're going to have a colony on Mars, or 500 people in 5 years or 10 years, or 1,000 people, whatever. It seems to me that one of the big issues there is, how much confidence do we have, if any, that humans can actually safely reproduce in deep space?
Well, we know that mice have been born in space. I don't know if people say, I feel like I'm jumping in with all the answers, but feel free to jump in. Mice have been born in space. To our knowledge, there's not been no officially sex in space between humans that we know of. Mice.
Were the mice actually conceived in space too?
No, they were sent up pregnant. So mice,
right.
They actually have a vivarium. You can see the mice, and there's a camera, and you can see the mice floating around, and they're very confused. So we think it was not as romantic for the mice as maybe we would have thought. And but we know that gestations occurred, gestations progressed, and then birth did occur. So I think it's possible that it'll work. I just don't know how well it would work. I think you'd want gravity, probably.
I think the concerns there are part of it is conception, part of it is the very, very delicate developmental phase and potential for radiation and damage.
Yeah.
Aside from radiation, George, get back to the question you raised about, why can't we spin these things? I mean, is that maybe is that a possibility when we start looking at Mars and deep space? That I've often thought maybe the reproduction and that process takes place in a gravity-induced environment as opposed to the planet itself. Does that make any sense?
Well, I don't think it's I think it might be different for different animals, as Chris was alluding to. I think humans are adaptable enough they could probably do the entire process without gravity. But I think this redistribution of fluids and long-term osteoporosis and so forth, it's something that will, it might start kicking in after 5 years, or certainly after a lifetime. You asked earlier if we were going to evolve. Well, it takes forever to. What people forget about evolution is it's a pretty messy business with a lot of death, and that's just not real. A lot of premature death, I should say, reproductive death, and so I don't think that's what we want for humans. Now, human evolution has mostly been cultural for the last millennia, and so there's a cultural and technological option, and I think one of the kind of threads of questions in the chat have been in Q&A have been whether, how we do this ethically, and probably the way we'll do it is the same way we do current extreme medical innovation, which is through the Food and Drug Administration. I think the Food and Drug Administration should have perfectly fine to have jurisdiction in space, and these things. The problem is the N is small. The number of people that you can get is going to be small. But still, that's how it's going to happen. You're going to have to. Ideally, you would have a randomized, blinded, control groups for these things. I was fascinated by what Chris Mason said, that not everybody gets OXO-G. Is that, and probably that's true for many of the parameters.
Yes, yeah, exactly.
So if we can leverage that either genetically or some other way. I mean, genetics is turning out to be a fairly cost-effective and precise way of developing drugs. And we just set a record for a gene-based drug or vaccines, at least 3 different vaccines that were produced in a short period of time and with very, very safe track records so far. So I think it's going to be something along those lines.
We may, I imagine that as time goes on, these trials and these studies will become better, because I think a number of agencies and organizations have put a lot more emphasis on including many more communities an opinion. And I believe that whereas in the past there was a lot more a sense of, we know this and we will let you know. And now there's much more a sense of, let's have a conversation and have a community decision. Now, it's unlikely we'll all agree to do one thing, but at least there will be inclusion and discussion. And I think that will help a lot in having some progress, certainly in having people feel part of the process. I think that's a big piece in taking steps with regard to genetics.
That's a great point. And even just the view of the flight surgeons and the astronauts has been historically a bit contentious, because the astronauts are worried the flight surgeon might find something that would ground them. And so most space agencies have been pretty reticent to bring in modern molecular genetics or even precision medicine into the astronaut corps for fear of that they would find something that would ground someone. But most of what, there's ACMG is now up to 71 genes, I think, that you can say are truly deeply actionable. And a lot of the other ones are just risk factors. And so I think instead of viewing these as metrics like cell-free DNA metrics or genetic factors that could ground someone, they could be just help guide someone's care or even treatment or just long-term risk management. So I think that's starting to change, and certainly it's being pushed to the side by a lot of the commercial and private astronauts. They aren't under the regulations of governments, so they can do what they want, which I think, and most of them so far have been really pro-research.
I think also,
wouldn't it be interesting if instead of grounding them, it actually helped them get up there? They're disqualified for some bogus reason, and then you find out, well, actually they have better
beneficial
protection against radiation, et cetera.
I think also as plans for space events goes into the years or decades or longer time frame, people realize that genetics gives you an idea of your predisposition for things that might actually foil an entire mission. So the idea is not, will I be able to go up into space for a week? It's, will I be able to complete the mission 30 years from now? And that has changed people's attitude towards the usefulness of genetics. Sort of mission-oriented reasons.
Somebody asked a question about, I'm not familiar with this, the JAXA zebrafish experiments. Is somebody familiar with that?
Some of the, I was looking for intergenerational, I think, epigenetic changes.
Yeah.
I don't know if those have been published. I remember hearing about that mission, but I'm not sure. It was looking for, there's some really great work by Oded Rajavi who's looked at intergenerational inheritance, actually even of small RNAs that are responding to viruses. And there's a lot of epidemiological evidence on epigenetics being transmitted through generations, but that study was supposed to look at it in zebrafish, but I don't know if it's been published yet. Oh, there's a lot of questions. Which ones? I guess Chris, I'll leave it to moderator's discretion. Which
No,
ones
go ahead. Feel free. Whatever you guys. I'm glad you're looking at them because there's a number of them that I see a question here from Scott Solomon, who's done some work into evolutionary issues with space, how people evolve in space, important to distinguish between acclimatization and within the individual's lifetime and evolutionary adaptation over generations.
Well, one I'd mention is one I spent a good half a chapter in my recent book about this, was the silver fox experiments. And I don't know, actually, George and Ting, have you heard of these experiments? Or
yeah, sure.
Yeah, one of my favorite, because it was only the first, for people who don't know, it was a Russian genetics experiment who was in the 1950s saying, let's take all the most tame silver foxes and only breed those, and the ones that are aggressive and mean, just let them die of old age. And within even just about 20 years, 30 years, they started to see phenotypic differences like floppy ears and a shorter face that made them look like dogs, and really amazing rapid evolution that was over decades. Normally we think of evolution taking thousands, tens of thousands, or millions of years, but it's one of my favorite examples. Actually, again, I'll put it in response to the question because I don't think there's a general chat box, but it is certainly evidence that evolution can move quickly if you do it in a very focused way, I'd say. I'll put it in the chat box here.
There's a question here also from Gina Loring, who I have met before. Since we're talking about sending more organoids to space and looking at pluripotent stem cells in the ISS, it's interested is, do we think there's anything, we'll learn anything from that work?
Yeah, so I think organoids are going to have many fewer of the problems that a whole organism would have. So from that standpoint, I think, mice and humans are better systems. You got immune systems, you've got the vascular flow, you've got psychosocial. There's all kinds of things that organoids won't do, but that it's a good way of testing things. If you want to see the impact that, say, radiation or microgravity has on humans, it's a much more ethical way to start. You start with, that somebody else asked about whether we're going to have poly P53. Well, I think we should have poly P53 in organoids before we have them in people.
Yeah, and there's the eLife paper. I'll put it in the response. It was like the elephants that have many more copies of it. I'll put this paper in there.
Right. But we don't really know what it's doing in elephants. It is true, elephants have lots of cell divisions without things going off the rails, but there are a lot of other larger organisms that don't have poly P53.
Right. And most don't, actually. So it's kind of unusual that the African elephant does, actually.
A number of questions, as you can see, come in about electromagnetic fields, radiation, those kinds of things. I know I've seen both discussions of ways to shield and also ways perhaps to genetically manipulate where humans can withstand that. Where are we on all of that in terms of progress? Because that obviously is a big one.
to a recent NASA sponsored meeting, like a think tank meeting, to discuss this issue. And I came away with the sense that this remains one of the two most difficult problems for long-term work and play in space. And the ideas that were proposed at that meeting were really interesting, but I don't think anyone left feeling that there was a solution to this. I think radiation damage and also the psychological effect of being away from society are considered, I've been told multiple times, that those are the two things that we need to really address in a serious way.
Mm-hmm.
My personal feeling is that, I guess, theoretically, you could bring up enough shielding, but it's not practical at the level that we might want it to be. So I turn my attention to genetics. We don't know the capacity of what cells can do to repair themselves, but there is so much work going on right now all over the world in trying to understand the repair system that I can say with confidence, it's probably worth exploring that area. Whether there's going to be an answer there or not, I don't know. There are definitely some people who are more sensitive and not able to repair their DNA, and there are some who seem to be very good at repairing their DNA. Maybe we could work on that.
Chris, back also, something that Ting just talked about, alluding to some of the which I agree with, psychological issues of being separated and, being in a, ship for 5 to 7 months. Were there any the twin study and things, has been any neurobiological that go beyond, a physical, that are also manifested themselves in psychological issues?
Yeah, the analogy being the gears of the clock we saw were disrupted, but what did the hands of the clock do?
Right.
It's actually an analogy that Matthias Bosner, who's from UPenn, was also one of the PIs on the twin study and worked with them on other missions. And almost every astronaut we look at, they have some cognitive decline in flight. Scott Kelly did not, though. He actually did in some metrics better for accuracy and speed in flight, but there's a battery of cognitive tests that you can do on an iPad that are now one of the standard measures for NASA. And most people do worse in flight, but occasionally, like Scott Kelly, he actually did a little bit better than what he was doing on the ground. But then when he got back, he did worse. So there are some questions of, and even outside of a baseline, so you can use your own enough time points before flight to get a baseline. So there, much like I think for the molecular measure, some of the cognitive traits do also depend a little bit on the person, and that's the measure that we've been using the most, I would say.
So the only ethical thing to do is to let Scott live up there as long as he wants.
That's right. That's right. Which he has volunteered. He actually recently sent me an email. Actually, two really interesting exchanges with astronauts recently. One is Scott just said, "Is my body still useful for science?" Which I was like, well, of course it is. It's because they're planning additional missions maybe with Axiom, so he might be, and we're still doing blood draws for him as well as his brother, now Senator Kelly. So. So they're very humble and very, they're happy to help science, which is always wonderful. But then one other interesting question came up when I was presenting some of the clonal hematopoiesis data of slight mutations that were appearing that are changing their frequency in the blood over years. Was one of them, this came from Mark, who said, well, can't you just like CRISPR away the mutations and put them back the way they were? Which I thought was great, because I was like, well, not yet in people, but like in mice we kind of can, but not perfectly. But there's prime editing, so I gotta give this long answer of like, not yet, but stay tuned to someday we could fix what mutations you picked up in space, but or from anywhere for that matter. So I thought it was a very interesting question from a very pure patient or astronaut perspective. Like, well, if you're looking for mutations and you find them, dear geneticist, why can't you fix them? And so I think I said not yet is kind of what I answered.
But we're a lot closer now than we were 20 years ago.
Or even 5 years ago. Yeah, it's really, yeah.
One thing you can do, it's part of it's a delivery problem. One thing you could do is you could replace your whole hematopoietic stem cell system. Yeah. That's by far the most common transplant, and it has impact throughout your body because they circulate and contribute to all of your red and white blood cells. So that's
can you explain that a little bit more? That's kind of interesting. What that entails.
Well, we know how to do hematopoietic stem cell transplants, and those cells go on and differentiate into a whole host of different kinds of cells, and they're distributed by your blood. So that would be a way of replacing damaged cells with undamaged cells, not by going in and editing each base pair, but by just replacing them with cell. Now you have to make sure those cells haven't been damaged. So you could keep them in tight shielding, or you could have them shipped up on a regular basis. But the point is that it shows an alternative to editing.
Well,
the problem with editing is getting them to the right cell at the right time. That's very challenging. But
open chromatin, that's like, yeah, that would be, what if it's, closed when you get there?
It's a needle in the haystack, because you don't know which cell has been damaged until it forms a tumor, and then you know which one was damaged. Yeah.
I guess you could think about this it's three ways. There's prevention, there's fixing, and there's management. Prevention is complicated. Fixing right now, we're working hard, but we're not there yet. But management is something that involves detection and then taking care of it. So you can manage many diseases so the person's perfectly functional. And I think what George just mentioned is a form of management. You did not prevent the problem. You did not fix the problem, but you managed it by replacing the blood system. And so this is it's an alternative way that may actually be more practical in some cases.
That's pretty interesting. Ting, I'm going to go back to something you said. I think you alluded to this. You alluded to some separation from society. I think that's part of that is really mental health. Obviously, there's neurobiological connections, but I think we really don't. I would like to maybe talk a little bit more. Have you talk a little more about, we have no precedent that we can go to look at for the kind of psychological stress, mental stress that people are going through when we're talking about Mars.
I probably am not the expert in this area, but I will say that I've, and this, Chris, this may be not exactly addressing what you are talking about. Through the Personal Genetics Education Project, we talked to a lot of different communities about how they feel about genetics. And we often refer to the enticement and the danger of traveling in space. And what I see in a room, let's say, of 100 people, is the surprising and very inspiring group of individuals who are willing to put up with very stressful, very adverse situations for the purpose of exploration, for the purpose of seeing if somehow humanity can be helped by accepting a certain amount of suffering. And I find that kind of dedication not only inspiring, but I think underlies a lot of the explorations that people do physically, but also in science, in politics, and economics. So in those discussions with these individuals, what we see is a recognition of all of these problems, but the knowledge of it, preparing them to deal with it, even though there's no obvious solution. And I wonder if that carries through for a lot of the astronauts that we have and the people who are willing to do this. Now, I'm going to jump to the use of genetics, bring it back to genetics. Very often in a room like that, we'll have people say that if we don't bring in space, that they are very anti the use of genetic editing and genetic technologies. It doesn't fit with their family. It doesn't fit with their belief, their faith. It doesn't fit with their sense of equality. But very interestingly, when we bring up the issue of protecting astronauts and explorers who are already taking on a lot of burden to do exploration, the issue of protecting them in space, it is really astounding. And I think I'm underestimating 80% of people who are adamant about not using genetic editing on our planet agree that we need to protect people however we can who are taking these steps in space. So I didn't address how people deal with it. I don't know what the medicine for taking care of it, but there is this general sense of societal support for people who are willing to take those chances.
There's a question here too about from Tiffany Vora, who's been very involved with humanity in deep space, parallels between space physiology and longevity challenges and how these things may intersect.
Yeah, I'll start on that one, since I do work on longevity, or we call it aging reversal, because that's easier to document for the purposes of the FDA approval. there are many of the things that like radiation damage do set off epigenetic effects in aging and during the course of development and aging, and some of those can be reversed. The epigenetic components, the genetic components often don't need to be reversed unless they cause cancer, in which case preventative action is strongly favored. So yes, there are a lot of shared interests, and I think there's a lot more justification for or more funding available for aging research, because it impacts all kinds of diseases that cause even medium onset, that is to say, things that affect people still in the prime of their life. And so I think, and with the aging society, there's quite a bit of funding set aside for avoiding cognitive decline. And those same sort of some of those will act by general core mechanisms that are shared by all forms of age-related diseases and all forms of sort of stress-related diseases, as you might say, are a lot of the space-related problems.
Like big spikes in inflammation markers can drive clonal metapoiesis and even mutated clones to become more abundant. Or I can tell at least a few answers, though, that at least for the epigenetic age, he stayed relatively flat, so we didn't think they got epigenetically younger. The telomere lengthening is kind of younger, but it went away as soon as it got back to Earth, and then there were more damaged telomeres upon return to Earth. So I think that is more of an effective low-dose radiation sweeping out a lot of the cells that were close to dying, we think, is probably one of the effects there, and also priming the immune system to begin scavenging. So I think that they're related fields in the sense that anything we can help with, reversing aging on Earth should probably help all those astronauts. But a lot of those changes in the body that we observed are not necessarily permanent or even necessarily, I think, showing big fountains of youth in space. But the telomere lengthening story is kind of a cute way to say the fountain of youth is in space, at least temporarily, in a way, I guess I'd say. But when we looked at other metrics like stem cell function, epigenetic age, telomere length is the only one that's really kind of younger.
In the few minutes we have left, I want to talk about something that we found intriguing. This is, by the way, Scott's book. I promised I'd put it up. The next 500 years, life to reach new worlds. It's really quite good. I read it, and I highly recommend it. I like it because he weaves in philosophy and lots of other issues. In fact, that's what I want to talk about, Chris. One of the things that I read early in your book, which struck me as really interesting, and something I quite frankly had never really thought that much about, gets into the ethical issues of space, and should we be going to space and leaving the planet, and should we be focusing things here? And you bring up this issue that humans are the only organisms on Earth that we know of that understand the future, can deal with the future, can predict it, and can change it.
Yep. And
that we have an obligation beyond just our species. There are lots of other species on Earth which are depending upon us kind of getting a handle on this. And again, that both goes to space and climate change and what we do to the Earth. So I just found that really fascinating ethically and philosophically, and it's something I'd never really thought much about.
Yeah. Oh, thanks for bringing it up. And also, thanks for plugging the book. Very much appreciated. Also, I thanked both Ting and George in there. And George, thank you for writing a blurb for the back panel of the book. Very appreciated. I talked about some of the meetings we've been in together in the book. So it was fun to write the book until I got to the last chapter where I talk about the end of the universe and should humanity take this genetic duty, I call it, a deontogenic ethic, as I look, what is your duty as a species? And most people have a hard time finding a duty just for their own life. But I think this is one of those duties that is activated the moment you understand it, which is extinction. Is that we can actually understand it and then even prevent it. Of course, we can cause it. But this, I think, gives us a duty that is innate to our entire species, or it doesn't have to just end with us. Any species that's sentient and can project into the future and understand extinction also, I think, should have such an ethic. Even machines, if an AI system takes over, I'm hoping that an AI might be benevolent and think, oh, we should serve as caretakers and guardians of species and life, including non-carbon based life. So I say I'm matter agnostic towards cognition. So whatever it might be, I'm hoping that the cognitive state has some sense of a duty towards life in all its forms. But I really mean it, is that we, this is and actually this is something that the Revive and Restore project that George worked on. I just recently joined that group, and it's a great idea to bring all the modern tools of molecular biology and genetics to save as many things as we can and preserve them, even in some cases bring them back. And so I think it's really extraordinary time, and I view this as like my life's calling. I think it's actually our species calling. So I tried to define it an ethic that it was before Kantian or utilitarian ethics that is antecedent, because if you don't exist, you can't have any ethical system. So it's like the preceding ethical system is based on survival, which is a very minimal ask, but along the way you can serve as caretakers for all species.
Any other thoughts, comments about that from Ting or George?
Well, I think the end of the universe goes a little bit beyond his 500-year, hopefully. Hopefully anyway. And I think I think we will, if we survive the next 500 years, we've got a good chance of changing our view of how the universe ends. I think right now we have maybe a little humility about something that far off. I've seen estimates of 10 to the 100th years, 10 to the power of 100, and so that far out, all bets are off as to what the real physics is when you have a galactic or larger intelligence working on it.
Okay, well, listen, we are out of time, and I promised we'd end on time. So I want to thank George, Ting, and Chris so much for your great conversation. And again, we did record it, so it'll be available on our YouTube channel. Those of you who want to continue the conversation or maybe leave some comments, you can always go to humanityanddeepspace.com and leave thoughts and comments. And there's always a series of articles on there to hopefully stimulate your thought a little bit more about these and other kind of topics. So again, and thank you to all of our sponsors. And this has been a really, really interesting, enlightening conversation. I look forward to learning more about it. So from Humanity in Deep Space and our sponsors and our speakers, thank you so much. And we'll see you for our next forum and webinar.
Thank you, Chris.
Thank you, Chris. Thanks, George. Good to see you.
Good to see you.
Thank you.
Yeah.
I hope you enjoyed this latest episode of the Humanity in Deep Space webinar series. We'd love to hear from you. You can always check out humanityanddeepspace.com, which is our website. It's also an opportunity there for you to leave comments and your ideas. And we very much want you and welcome you to let us know what you thought of it and any ideas you might have for content for the future. Thank you.